I think so. They've never seen a bald guy, I guess. Bald by choice, not by force. Maybe. So I think the main reason they're really scared the whole situation is that they sign up for the class with Odell, and we had to change the instructors because of the time conflict. And they ended up with me.
Yeah, Odell is quite easy. You dumb it down a lot.
Yeah.
The exams like exactly like the homework and stuff.
Yeah, and I don't do that.
All he does is examples. And,
Yeah.
But the end of the semester, you've got 120 examples on the same topic, so and that's the exam. Those same things.
You can do those examples really great, but the theory behind them is kind of lacking.
Yeah.
Right? I feel like you're the exact opposite. You know, do a ton of examples, but the theory is pretty locked in. You know?
Okay, that's thanks. Yeah, you want to be somewhere in between, right? But we don't have enough time, unfortunately, and we don't really offer teaching assistantships to our students, right? If I had a TA for this course, I would have dumped all of the example solving onto her or him, and then we have just covered the theory. Okay, so I'm sorry to the online people. So I apologize if the sound quality is not as good as the previous lectures because my mic ran out of battery last night in the middle of the lecture, another lecture, and I forgot to charge it. And my AirPod doesn't work, so you're stuck with the laptop mic. Okay, so let's talk about from next lecture, since you guys don't really show up early to your class, whoever is here at 10:05 will get a bonus point, right? Yeah. I do whatever you guys do. What's that?
We're here at 10:05.
I mean,
Next time.
next time, yeah. I mean,
Just stay at 300 main the whole day.
Just like we'll wait all in this class.
You should make it first person who gets a bonus point. So we gotta wait at the
You're gonna have to
door
run
in
it all the way
line.
from Lagrange.
let's actually do that, huh?
You're gonna have to run it from Lagrange.
First person who's here.
Oh, God.
You can log in on Blackboard. You don't have to be here. Just on your
Oh,
phone,
that's
just log in on Blackboard. And then count as
8 a.m. I'll be.
Okay, let's focus on the course material. We can always come back to these discussions. One thing that I want to mention is that we only have 4 more lectures. Is that correct? Yes, we only 5 more lectures. Yes, 5 more lectures and an exam, right? Your exam is going to be on April 22nd, which is the last class, right? What we can do, if you think that's a better idea, we can move the exam to an earlier time, right? To have a little more room between your finals and the second exam. If you think that's if this is something you like better, right? As far as I'm concerned, yes.
If we moved it up, would we have like a review day for the final, like comprehensive, like?
That's the idea, right? That's the idea. So as far as this course material, we only have to cover one more chapter 3, and we'll be done, right? I mean, I wanted to cover more. I always want to cover more, but up to end of chapter 3 is the material we need to cover, right? And there's another chapter, interplanetary flight, that I really like to talk about a little bit. And we will talk about it. Chapter 3 won't take more than 1 lecture or 2 lectures. Right? And we are at the end of chapter 2. We're gonna finish chapter 2 today, that's for sure. And so if you want to move did you want to say something? You had your hands up.
Yeah, I was wondering if like the option was to skip the review day or skip interplanetary travel, because I would rather.
We're not gonna skip anything. We're just gonna move things. Yeah, we're just gonna move things. It's not just so. If we move the exam to next week, for example, your exam 2 will be only chapter 1 through chapter 3 of the orbital mechanics book. The rest of it will be covered in the final, right? We are not gonna exam you. I'm not gonna test you on something we haven't covered yet. Okay? I guess that's given, right? Yeah, and so we don't. I guess we need to decide about it right now because it is pretty close, right? So what do you think? Do you wanna keep the exam as is, or do you want to move it to an earlier date? We have everyone here except Nirlep, I think. Yes, Emery, Steven, Lawson is also not there. And not Lawson and Nirlep. What do you guys think?
So if we move it to an earlier date, interplanetary travel won't be on it, and then we'll just learn interplanetary travel after, and it'll be on the final.
Yes.
Yeah, I think that sounds better, right? Because then
Would we,
it's only on the orbital mechanics part.
yeah, if we didn't move it, would we lose that like review day that people stuff?
We will do a review day anyways, right, before the exam, but it will be mostly. So we will do a review day for only exam 2 then, right? Not the comprehensive. Or it's a review day, so I will review whatever you want me to review.
But like you said, it's probably focused on exam 2 since that's all we have.
Yeah, because it's just 2 classes before the exam 2. So.
Otherwise, we'll have both to cover after we do the exam 2.
Honestly, I don't think you guys need a review day based on unless you have cheated on your exams, right? That's based on what I've seen from your exams. There was one problem that a lot of you couldn't figure out on your exam, and I mean a lot of the problems you didn't like finish the solution or you had the wrong final answer. I just gave you the grade, right? I usually grade your exams like this. I guess to be a little more deep. Yes.
Can we use Excel on the next exams?
Excel to do what?
Just for regular like plotting things.
For plotting. I'll make sure I'll give you shorter questions, right?
Okay.
I think that makes more sense, right? Than just you using Excel because, yeah, I'll make sure to give you shorter questions. Okay, so I think we are not gonna conclude anything today because you're asking, just talk amongst yourselves. I'm pretty sure you have a chat room.
Like the early one.
I think the earlier one.
Yeah.
What do online people think? I haven't received any feedback from them.
Less times we're tested on lunar trajectory, the better, I think, or interplanetary trajectory.
We are gonna do some, not trajectories, I guess. Yeah. Some. Okay. Learning towards keeping it, leaning. I don't really have a preference. We have one person who leans towards keeping it. Let's actually do this. So since we don't have a unanimous agreement here, you guys talk amongst yourselves and let me know on Tuesday, okay? And whoever is here before 10:05 will get a bonus point. So you have the option to get 5 bonus points.
Yeah, the person here earliest decides.
So I guess it's gonna be, and Nicholas has been consistently the earliest person in class throughout the semester. So I guess let's go ahead and start the discussion. We are going to talk about a couple of things. I'm going to, hopefully I'm not gonna go into the derivations and the proof of the theory. I'm just going to mention the theory, give you the equations, talk about it, and we move on. And I say hopefully because I usually get sucked into the derivations. That's my nature. But we are going to talk about perifocal frames, then the Lagrange coefficients. Lagrange coefficients. And then a special type of a three-body problem. Three-body problem in which we will focus on Lagrange points and Jacobi number. This Jacobi number is a very, I guess, important parameter in designing a spacecraft who wants to escape the gravitational pull of Earth and Moon. Right? What is a perifocal frame? The perifocal frame is a natural frame. Natural frame. Which essentially is a Cartesian coordinate system. It's a fixed system, so not moving, and its center is on the focus of the orbit. So what does it mean? It means that if this is your whatever elliptical orbit, let's actually make it more general. Let's say this is your orbit, M1 and 2. Its center is located at your focus, and X is on the half line, X coordinate, Y is perpendicular to the half line, right? And then we also have a Z coordinate that is going out of this bolt, right? The Z coordinate. The unit vectors in each direction are going to be called P hat for X, Q hat for Y, and W hat for Z. You can define your R as X hat P, X bar P, as Y bar Q hat. And the relationships between the cylindrical coordinate systems and the Cartesian coordinate system are applied here. So your X hat is R cosine of theta, and Y hat is R sine of theta. We have already said that these two lie on the same plane, meaning that this orbit is essentially a two-dimensional thing, right? But why do we introduce a third dimension when we are talking about this perifocal or natural frame? Why do we do that? That's my question for you. What is the parameter that is in that direction? Direction normal to the board here.
Is this the like right-hand rule with the up vector outwards?
Yeah, that's the direction of the Z coordinate. Yeah, is that your question?
So like, does it? Never mind.
What is the parameter that is directed outward or inward, perpendicular to this natural frame? What is the direction of R? Right? Something like this, right? What is the direction of velocity? Tangent to the plane, right? Or R dot. Doesn't really matter. It's to velocity. What was that specific parameter that connected R, or that was calculated based on R and velocity? Or let me rephrase myself. How did we calculate angular momentum?
Is that azimuthal velocity?
Azimuthal velocity is in the same place, right? Right? How did we calculate angular momentum? What was the equation for it? R cross
M/R dot.
So the specific angular momentum was calculated as R cross V, right? So, which essentially means that the only parameter that it's the direction of a cross product is perpendicular to the both other parameters, right? The other two vectors, which means that your angular momentum is in this direction, right? So that's the only parameter we have. And we can find the unit vector in that direction by dividing the angular vector momentum by the magnitude of the angular momentum. You can actually find the vector form of the orbital equation using the natural frame as there, h squared divided by mu, 1 over 1 e cosine of theta, multiplied by r hat. That was the main equation for the hat. We can substitute that with cosine of theta, p hat, sine of theta, q hat. Okay? Can also have the same formulation for v or r dot. It's going to be equal to x bar dot p hat plus y bar dot q hat. And if you do some simplification, these are all the equations you have seen before. I'm just giving them in terms of v hat and p hat. Mu divided by h, negative sine of theta p hat plus e plus cosine of theta q hat. So two main equations, velocity and r with respect to perifocal frames. Okay, so just a definition, it's just a definition, there's nothing special to it. Perifocal frames. We are going to use this type of framing a lot in the rest of this lecture. Okay. Specifically in defining the Lagrange coefficients. The idea here is that we are going to have an initial value for R. R naught, that's the initial value, and V naught for velocity and R, right? And based on these initial values, we want to find the value of R and V at a different theta, or at a different time, right? It is something you have done throughout your educational career a lot for different types of problems, but we want to do this in orbital mechanics, right? So in a perifocal frame, your R is going to be equal to x bar p hat plus y bar q hat. V is going to be equal to x bar dot p hat q hat. And we can write the same thing for R naught and V naught. It's going to be x naught hat p hat, x naught bar p hat, a lot of hats and bars. X naught bar p hat, and so on and so forth. Okay. So the idea here again is to use these two that are given to us and find this new R and V at a different time step. We have all of the orbital equations. We have a lot of things that we can actually employ here. And what we want to do with Lagrange coefficients is to simplify the calculations, if you will, to come up with some parameters that will help us just plug in some numbers and find the new R and V based on R naught and V naught, right? If you do the analysis, you will get to these two main equations that relates your R and V to R naught and V naught, right? Need F, that's one Lagrange coefficient, R naught plus G V naught, and V is going to be F dot R naught plus G dot V naught. So these four are called the Lagrange coefficients that are going to help us find the parameters R and V at a later time. But as I said, I'm not going to go into the proof of these. We are only going to focus on the final equations and the concepts. Again, the concept here is that these four parameters, Lagrange parameters, are going to help us find R and V at a different time, after some time has already passed. Okay, so, well, what are these for? F is going to be equal to x bar dot minus, y naught bar, y bar, x naught bar divided by h. D is going to be equal to negative x bar y naught plus y divided by h. F dot is going to be equal to x bar dot y naught bar dot minus divided by h. And for G, we can say negative x plus divided by h. So if we find these four parameters, we can find R and V. Well, as you can see here, what do we have in these formulas? We have the presence of x bar and y bar, which are essentially the x and y in the future point that you're looking for. So this solution is not very helpful for us, right? Although these are the Lagrange coefficients, these are the first thing they derive, but it's not very helpful to us. So what we can do, what can we do to eliminate this problem, to essentially only have one parameter from the second orbit, which is going to be the true anomaly, right? And then find it out. So what we want to do is to find these four coefficients based on delta theta, right? The true anomaly. Which theta is the true anomaly at the second position. This is something we need to have, we have to have, right? Because we want to find R and V at the second true anomaly. That's the idea, right? That was the first thing that we started this whole thing. And theta naught is also given to us, right? This is something we already have. Okay? So, plug in the values again. Your F based on the delta theta is going to be 1 minus mu r divided by h squared, 1 minus cosine of delta theta, right? Here G is going to be equal to R naught, sine of delta theta, right? And your F dot is going to be equal to, this is a long equation, mu divided by h, 1 minus cosine of delta theta divided by sine of delta theta, multiplied by mu divided by h squared, 1 minus cosine of delta theta, minus 1 over R naught, minus 1 over R. And we also have a G dot here. The new G dot is going to be 1 minus mu R naught divided by h squared, 1 minus cosine of delta theta. Okay. So, what are the parameters we have here? We have delta theta, which we can easily find, right? This is essentially given to us. We have R naught, which we can find based on the orbital equation, right? But there is one more thing that we don't have, and it's a little bit finding it is going to be a little bit harder for us. R, right? It is the magnitude of this vector, right? This future vector. So we have another equation for that magnitude of the future vector that I'm going to write here. That we can find R using something that is similar to the orbital equation, the main orbital equation, but only uses delta theta. Doesn't use theta for that matter. Cosine of theta, this is minus, all of this is in the denominator. H, we are not divided by mu, sine of delta theta. Okay, there are a lot of equations here, as you can see, and a lot of long equations. But as long as you have the equation, you can plug it into Excel or whatever and get the numbers, right? Which essentially means that your life is going to be much easier. But let me ask you this one thing. How can we calculate this VR naught? VR, right? We have azimuthal and radial velocity, right? VR, how can we find VR? VR naught. the idea is we have the vector V naught, right? And we want to calculate VR using that. We had one equation that was mu divided by HE sine of theta naught. Right? That's one equation we had, but for that equation, you don't need to have the V vector. If you want to use the V vector, V naught, to calculate the VR naught, you essentially have to find a projection of V naught in that direction, right? In the R direction. So VR naught is going to be equal to your V naught vector, right? Multiplied by the unit X vector in the R direction, right? Which is going to be R naught divided by R. Or you can simply just use the mu HE sine of theta naught. Okay, so you're actually going to come back to this. Let's actually do it right now. Let's solve an example. But before solving an example, take a look at these equations. We have this is given to us, as well as R and D, right? Some form of them is given to us. F, G, F dot, D dot, and these equations are going to help us find a future orbital position and velocity, right? Find initial value of that orbital position and velocity. What is a very important parameter that we don't have here? Just look at these equations. What is missing in these equations? In these equations that I have, this one, these three, and these.
Momentum,
Angular momentum,
angular momentum,
right? It is here. It is
eccentricity vector.
eccentricity, right? So we are missing the eccentricity, or we don't need to have, not missing, you don't need to have eccentricity if you use the Lagrange coefficients, right? What does it mean? This essentially means that we don't need to know what type of trajectory or orbit we have here. Is it elliptical? Is it circular? Is it a parabolic trajectory? It doesn't matter. Right? We don't need to calculate eccentricity, right? Which means that it's in some ways it's going to make everything easier if you don't need to determine what type of orbit you want to have. You just want to find the second position using the first position and initial position, right? Okay. If you get an example, right? There is example 2.13 of the book. Let's actually go over it very quickly. This is an Earth satellite moves in the XY plane of an inertial frame with the origin at the Earth's center, right? Relative to that frame, yeah. Relative to that frame, we have R naught. First of all, you are told that you have an inertial frame with the origin at the Earth center, which is your focus. So we are talking about perifocal frames, right? The first thing we discussed here. Your R naught is going to be equal to 8,082.4 I. It could have been P hat, but for whatever reason your book is not consistent here. It doesn't really matter. J hat and V naught is equal to 0.47572 I plus 8.8116 J hat. So we have the R naught and V naught, we are given. We want to compute the position and velocity vector after the satellite has traveled through a true anomaly of 120 degrees. What does this piece of information mean? The second one.
Theta is equal to 120.
Is it theta or delta theta? Delta theta, right?
Delta theta, yeah.
So we are going to assume we start at a specific true anomaly, then we travel 120 degrees, right? Just have to make sure that you don't make that mistake. Okay, so delta theta is given to us at 120 degrees. Okay. So what do we need to find here? It's Earth, so we should have mu, right? Mu is going to be equal to, it's usually given to you, the mass of the Earth. Let's see. What do we have? Yeah, that's 398,006. 398,600, right? That's the mu of Earth. Usually memorize that 300,000 and 98,600, however you should say it. Okay, that's the mu is given to us. What else do we need? We need to calculate the magnitude of R naught. How do we calculate that? Yeah, the vector. Pretty simple, right? You can calculate it. What else do we need?
Angular momentum.
Angular momentum. How do we calculate angular momentum? There was a relationship between angular momentum and the azimuthal velocity and the position vector, right? And that equation was, if you don't remember, R V azimuthal velocity, right? How can we calculate V azimuthal velocity? We have the VR, we have the V, and we can calculate VR using this equation, right? Just the dot product of V naught and R naught divided by the magnitude of R, right? And how can we calculate azimuthal velocity from that?
H over R.
We don't have the R yet, huh?
Oh.
But H over R.
Oh, this is for.
Let's actually do this.
This is for concentric. Sorry, that was because V is equal to V azimuthal, so it's the same. Never mind.
So we have the azimuthal for. We don't have the azimuthal. Is going to be equal to the square root of V squared minus V R squared, right? Right? It is simple. It's just a vector relationship. And we can calculate VR here. We are given the velocity vector here, right? Just plug it in here, and you have the azimuthal velocity, which means that you have the angular momentum. So we have angular momentum, which means that we can find R as well, right? For those equations. Then you plug in your main equation to find the Lagrange coefficients and find the new velocity and the position vector. Is this clear or is it confusing?
It's clear. I just lost the equations.
Okay. Clear? Clear?
What about the V?
Which V? This one? Okay. These are V naught, right? So we are given the V naught. But V, eventually, V at a future point is the thing that we want to calculate, right? So you find the Lagrange coefficients, and then I gave you the main equations you needed, right? FR plus whatever. R equals to FI at X bar. And those two equations, those two main equations I gave you. Any questions? I will upload your homework today, right? It was I wanted to upload it on Thursday, but at the time I didn't know I didn't remember that we are gonna have a wellness holiday. So you would have gotten these type of questions on Thursday without even going over it, right? So I had to postpone the homework to this week, and it will be uploaded either today or tomorrow, sometime this week. So you have the weekend to work on it, and then submit it. And then whenever you submit your homework 5 will be uploaded. Homework 5, right? Homework 5 will be uploaded as well. Okay, so one part of your homework will be to go over some parts of the book that is going to transform this from delta theta to delta t, right? So a time difference. So you will be given an R0 and V0, and I will tell you that this much time has passed. Give me the new position vector, right? But there's already long equations. I don't want to go over that in class. So you will get one question on the homework that will ask you to summarize that part of the book, right? So your assignment is going to be go there and read that part of the book. Okay, so let's move on to the circular restricted three-body problem, which is the last topic we are going to cover in this chapter. This is circular restricted three-body problem. So this is a special type of three-body problem, not a very general type one. We have another chapter on this, which I don't think we're going to get to this semester. The first thing you want to do is consider two bodies, M1, two bodies, M1 and M2. One is bigger than the other one. You want to put a co-moving frame on their center of mass. So a co-moving frame at which x-axis is on the vector connecting the center of mass of the two bodies. Y-axis is on the plane of motion of the two bodies, right? And z-axis is perpendicular to the x and y-axis. Okay. So the center of this frame is a co-moving frame. It's moving with these two bodies, right? Center of gravity. The only movement it has is a constant rotation, right? It's just a constant rotation. And we can find this rotation, omega, as 2 pi over t. You already have the formula for 2 pi for the period. Your period is going to be equal to 2 pi divided by the square root of mu, the position vector between the two center of masses, to the power 3 by 2. Okay? Which means that your angular velocity omega of that co-moving frame of reference is going to be equal to the square root of mu divided by R12 to the power 3, 2. Okay, so we have two masses. So far, it's only a two-body problem. We have two masses right? You have a gravitational force. We put a co-moving frame of reference on the center of gravity, and we are finding the relationships for these two masses. How can we find the mu here? Mu is equal to G M1 plus M2. We are going to use capital N for M1 and M2, so your mu is going to be Gn. And since we are putting the frame of reference on the center of gravity, its velocity is going to be zero. It's not going to move. And I'm sorry, let me just do this further. And its location is the center of coordinate system, so its location is also centered at 0. So for x0, we can find this relationship, and 1x1, which is this x, plus n2x2 is equal to 0, right? And the direction here is also important. So between x2 and x1, we can say x2 is x1 plus r12. x2, x1 is in this direction, right? And r12 is this. So x2 is essentially r12 minus x1, but it's a vector in the other direction, so it already has an negative value, right? Okay. Then, using this equation and these two equations, and by defining pi 1 and pi 2, which are a dimensionless mass ratios, we can come up with these two relationships. x1 is equal to pi 2 r12, x2 is equal to pi 1 r12. Pi 1 is m1 divided by m1 plus m2. And pi 2 is dimensionless mass ratios. So we have found the position vector of each of these masses for that co-moving frame of reference. Okay. Let's actually add a third mass here. A third mass, a third mass M, which real mass is very small compared to M1 and M2, compared to both of them. This position vector, let me use a different color. This position vector is R1. This position vector is R2. And then from the co-moving frame of reference, we have the position vector R. Okay? What does this remind you of? We have two huge masses, one of them is larger than the other, and we have a very small mass that is orbiting around the two. As you can see, this is essentially a three-body problem. You have three bodies, but one of them, its mass is very small. So that's why it's called the restricted three-body problem. It's just a special case of a three-body problem.
Is the really small mass so small that it's not affecting the orbit of M2 or M1?
That's the idea.
It's like a satellite orbiting the sun, but not the Earth? Or is it orbiting around? F2.
It's essentially a satellite that is orbiting around Earth, and also seeing the gravitational pull of
Oh,
the moon, right? That's right. If you bring in the gravitational pull of Sun, this is important as well in your analysis. And it will be a 4-body problem, right? Not a 3-body problem anymore. So we are only, at this point, we are only concerned with the satellites that are orbiting around Earth and Moon, the system, the Earth's Moon system. So R1 can be calculated as the x part of it is going to be equal to x minus x1 I plus yj plus zk. So the only part that is going to be difference, R would have been x plus y plus z, xi, yj, zk, but R1, its x is the only thing that is changing, right? We can do the same thing for R2. We can write R1 as a function of pi here to be x plus pi R12, I plus yj plus zk. We can do the same analysis for R2. R2 would be equal to x minus pi 1, pi 2, R12, I plus yj plus zk. So we have the position vectors, and I already said R is xy, xi, yj, zk. We have the position vectors, which essentially means that we can find the r dot and also the acceleration. If you recall, since this is not an inertial frame, its unit vectors are going to move as well. So we have to include those in the analysis too. So we need to go back to the dynamics of point masses or circular masses from chapter 1, which means that your r dot is going to be equal to velocity of this frame plus omega of the frame plus r plus r dot relative, v or v relative. Now, this is something we have seen in chapter 1 and also in dynamics, right? We already know that v relative is x dot I plus y dot j plus z dot k. That was the idea of the relative velocity. That's the relative velocity of this, velocity of m relative to your co-moving frame, not relative to an inertial frame. But this whole thing gives the velocity relative to an inertial frame. Okay? And r double dot, very large equations. These are something we have seen here. It's going to be a dot g plus omega dot r plus omega r dot and if you recall, we replaced this with omega cross omega r plus 2 omega v relative, and all of these are vectors plus a relative, all of these plus. Your velocity vector, your acceleration vector, but we already know that this co-moving frame is moving at a constant speed and also a constant angular speed. So we can simplify the equation to, let me rewrite it up here to have the a relative. So that's one part of the equation of motion. We have R double dot now, right? How did we find the equation of motion? In general, we said sigma F is equals to M R double dot, right? That was the idea, right? That was always the main idea. Okay, we have R double dot on one side, and we have two forces, F1 due to mass 1 and F2 due to mass 2. How do we find F1? That's G M M1 divided by R1 squared U R1, right? And negative G M M2 R2 squared U R2. Okay, which we have already seen in the earlier part of this chapter is going to be equal to mu1 M divided by R1 third multiplied by R1 and mu1 mu2 and R2 cubed R2. Okay. Is there any question here? Right? These are the things that you have already seen. We probably could have. Okay. So what would be the final equation of motion here? M R double dot, which is this, is equals to sigma F, right? M's will cancel out from the two sides. So your final equation of motion is going to be equal to R double dot is equals to negative mu1, which is dm1, divided by R1 cubed, R1 minus mu2, R2 cubed, divided by R2. This is the general form of the equation of motion for a circular restricted three-body problem. Okay. And that's the best thing we can get out of it. We cannot simplify this further. There is no, let me actually rephrase what I said, there is no closed form solution for this equation of motion. We already have the values for R double dot and also R1 and R2. We have these vectors, we can put them in and have the equation of motion in different coordinates, right? X, Y, and Z, right? So we can have three different equations of motion, but we cannot really solve it any further without making some simplification. Let me actually give you these equations, the final equations in each direction. So let's just write the three equations, and then we'll go from there. Let me start by X. So this will be the equation in the y direction. X double dot is going to be equal to minus 2 omega y dot minus omega squared x equals to mu1 divided by r cubed, r1 cubed. There's a negative sign as well. X plus pi 2 r1 2 minus mu2 r1 cubed x1. This is x1. X pi 2 r1 2. Okay, this is the equation in the x direction. In the y direction, the equation will be a little simpler. y double dot minus plus 2 omega x dot minus omega squared y is equals to mu r cubed y minus mu 2 r2 cubed y. And in the z direction, z double dot is going to be equal to negative mu1 r1 z minus negative mu2 r2z. So that is essentially the same equation of motion, just broken into its components. Again, we have no absolutely non-closed form solution for this equation of motion, for the restricted three-body problem. So what we can do, though, is to use these equations of motion to determine the location of equilibrium points and some other parameters instead of finding the real orbit, right? We cannot find the real orbit. That's the idea. That's what no closed solution means, right? These equilibrium points, are we all following? It gets boring after some point, all of these equations. And I understand that one. Because that's orbital mechanics is boring. Okay. After some point, equilibrium. So the next step is to find the equilibrium point or the Lagrange points. Use this. So we have the equation of motion for the three-body problem. Next step is to use this equation of motion to determine some parameters. We cannot determine the orbit equation, the total orbit equation, the whole orbit equation, but we can determine some parameters. One of these parameters are the equilibrium points or Lagrange points. So it's different from the Lagrange coefficient. Lagrange was an active person when it came to orbital mechanics. A lot of things are named after him. So yeah, let's make sure don't be confused. But what are these equilibrium points or Lagrange points? Equilibrium points or Lagrange points are the points where have the zero velocity and zero acceleration. So these are the points where if you put your third mass in those points in these two orbits, in two-body orbit, for example, that point mass won't move, right? So if you are standing on Earth or on Moon or on the center of gravity, if you look at a mass, that mass won't move. If you are in an inertial frame, that mass is moving in a circular pattern, in a circular orbit. But from these points of view, that mass is not moving. And that is called a Lagrange point. There are actually multiple points you can find. There are multiple. It's not just one point. There are 5 points in this specific case. But how can we find these 5 points? Pretty easy. The acceleration and the velocity has to be 0. So what does it mean for these 3 equations? You have to put x double dot, y double dot, z double dot equal to 0. Same is true for x dot, y dot, and z dot. Right? If you put them equal to 0, you should be able to find a specific x and y, or 5 x specific x and y's for that matter. Which again, if you plug in those numbers, you will see that that is also not possible without an iterative method. Okay, we can only find 2 Lagrange points. using this simple method, and these two Lagrange points are the point 4 and point 5, L4 and L5. How do you find L4 and L5? It's x is equal to R12 divided by 2 minus pi 2 R12. Its y is going to be equal to plus minus the square root of 3 divided by 2 R12, and its z is going to be equal to 0. So these are two of the Lagrange points. For L2, L1, L2, L3, you have to do an iterative analysis. You have to use it's a very complicated, not a very complicated, but it has a lot of mathematics involved in it. You can find the Lagrange points. Okay. We have put the best for the last. Jacobi number. Jacobi number is actually a very important parameter when it comes to circular restricted three-body or Jacobi constant, circular restricted three-body problem. We have the equations of motions. What we want to do is we want to find the living force equation for this three-body problem, for this specific circular restricted three-body problem. What was the living force equation? Who remembers?
Sounds cool, I don't remember.
Living force equation was essentially the energy equation, right? This is something we saw earlier, right? It is called the living force equation. It's actually called a French name. I don't remember the French word for it, so the English translation, the boring English translation, huh? Living force equation. It's essentially the energy equation. What was the energy equation for a two-body problem? We had the kinetic part of it, right? Mu squared, V squared divided by 2. We had the potential part of it, that's mu divided by 2r, equals to your epsilon, that was negative mu divided by 2a, right? That was the idea for the two-body problem. So we have a three-body problem here. We want to find this living force equation. Of course, we are not going to go over the derivation. I'm just going to give you the final equation. You're going to have v squared divided by 2 minus, that's the velocity of this mass, right? Minus 1/2 omega, that's the angular velocity of your center of coordinate system, the co-moving fringe, x squared plus y squared minus mu1 divided by r1. That's the potential from the first mass, the first big mass, minus mu2 divided by r2 is going to be equal to a constant value c. Right? In the other case, we had a constant value epsilon, which was a negative value for what type of orbit? Who remembers?
Hyperbolic.
Why is it a negative value? So a specific energy of your mass M2 that is orbiting around whatever, right, is negative. What does it mean? What do you get from that?
Is that a decaying orbit? Is your specific energy decreasing?
It is not decreasing. A specific energy is negative. It's a constant value negative. So your mass M2 has a negative energy. And
I thought negative energy wasn't possible.
But we have talked about this, right?
Negative energy?
Yeah, in orbital mechanics. What does a negative energy mean here?
taking, the best I've come up with is taking energy away.
You're taking energy away. Okay. So let me answer the question. We have actually talked about it, and it is very important for you to understand what a negative energy means. Negative specific energy means here. And negative specific energy means that you are stuck in the gravitational pull of Earth, right? That's why you have a negative spin. You don't have enough energy to escape the gravitational pull of the Earth, right? You will have to add energy, right? That was the idea, right? Then we got to zero energy, and then we got to positive energy. The zero energy meant that you can escape the gravitational pull, but as soon as you escape the gravitational pull, your velocity is going to be zero. What type of trajectory was that? Parabolic. And hyperbolic trajectory, you have excess energy, positive specific energy. The same idea applies here. And the C is actually, or in literature, some people use negative C/2. Right? So they divide everything and then put a negative sign. Here, it's called the Jacobi constant. Jacobi constant follows the same idea. Okay? Follows the same idea here. If you in these parts, if you move things around a little bit, you can come up with a formula for velocity. This is the magnitude of velocity. Is going to be equal to plus 2 mu1 R1 2 mu2 R2 plus 2c. Okay, this magnitude of velocity, this side of the system always has to be positive. That's the idea, right? Left-hand side, velocity squared, always positive, which means that this always has to be positive over 0. So we can come up with this inequality. Okay? This inequality is telling us that this value, or I mean, we can also say that your velocity value can never be negative. Okay? So the value 0 here is going to give us the boundaries of the no-go zone. No-go zone. I'm the one who's calling them no-go zone, which essentially means that your satellite orbiting around Earth and Moon cannot go into some specific regions, right? And those regions, how the area of those regions, how big or small those regions are can change based on the Jacobi number of that satellite, right? Jacobi number, how much excess energy or lack of excess energy it does have, right? That's the idea here. So obviously, if you have a very negative number, think about it this way. The idea of a negative energy was lack of energy to escape the orbit in a two-body problem. So a more negative number, what does a more negative Jacobi constant here, or Jacobi number here mean? It means that lack of energy to escape either the orbit of the Earth or the orbit of the Moon, or both of the orbits. So we have actually an analysis here that I want to show you, that is going to give us that this is in the book. Okay, so we don't need to worry about. Okay. You can see different Jacobi constant. You have a Jacobi of -1.8. These shaded areas are the areas that are impossible for a satellite to reach. So if you have a satellite with a negative 1.8 Jacobi constant, it cannot even get to the moon. Or if it's flying from the moon, it cannot even get to the Earth, right? So you have to make that Jacobi constant less negative. As you make it less negative, you can see these shaded areas are going to become smaller and smaller. And these L points are the location of your Lagrangian points. So with this value of negative 1.8, you cannot even get to any of the Lagrangian points, right? What was the Lagrange? The equilibrium points, right? That was the idea. And the value, so as you can see, as you make it less negative, you are eventually going to make this no-go zones smaller and smaller and smaller. And for a value of negative 1.8, 1.581, as you can see, your satellite can escape the gravitational pull of Earth and Moon and go out, right? And you can actually make them more positive until you get to this value of negative 1.6, which means that it is going to be easy for your satellite to escape the orbital pole.
So the negative 1.5683, it still has shaded regions over L4 and L5.
That's right.
Which are the ones we're able to find, right? Why are those shaded? I'm just confused why they make such odd shapes, I guess, my question.
That's essentially the effects of the gravitational pull of the moon, and that's a combination of the two. See, you start from this shape and two circles, right? You see two circles around them. Then these, you can see here that because of the combination of the gravitational pull of the two here, that is strong here, right? You can see these two are, the shape is different here, right? Then the gravitational pull of the moon is going to help you escape the gravitational pull of the whole three-body problem. That's right. So if you had another body here, I would assume it would have looked more symmetric, like a four-body problem. Yes.
So when you have all these Lagrange points, if your satellite, let's say, has a smaller negative value for the Jacobi number, if you pass through one of those L1, L2, L3, or L4, will it just stop there?
No. It already has excess energy, right? You have to calculate the energy. First of all, you have to determine the correct trajectory to send it there, right? You have to calculate the correct energy you need to get there, right? So if you have excess energy, no, it won't stop it, it will go. Okay? Is there any questions? Yes. Oh, you're already past the class time.
This is from a little further back. We were talking about the Lagrange points before. We were talking about the first time we brought Lagrange points up, you said they have no eccentricity value.
No, I didn't say they have no eccentricity. That was the Lagrange coefficients. We don't need to have eccentricity. That's the idea.
We don't need to have them, but what I was wondering is, like, if we do have all the other values, can we still find the shape of the orbit?
Yeah, sure.
Okay.
Okay, so that's it for today. See you all next week. Your homework will be posted sometime today or tomorrow. And that's it for chapter 2 of the book. And the stream, yes. And can you actually